Alright, we're going to talk about intermolecular forces in molecules, which means all nonmetal compounds. Okay, and so intermolecular forces, these are the forces between molecules. This is what makes molecules stick together to form liquids or solids. Now, there are three different types of intermolecular forces in molecular compounds, and these are the first two. Alright, the first one's a dipole-dipole attraction. In a dipole-dipole attraction, that's where you have polar molecules, and these polar molecules are attracted to each other by the positive ends and negative ends of those molecules, kind of like how magnets are attracted to each other. So one example would be CH3Cl, methyl chloride, and which we'll show you that later how that works. Another intermolecular force is a hydrogen bond. Now, a hydrogen bond is a dipole-dipole attraction, just like above, but it's more specific. It's a dipole-dipole attraction where you have a hydrogen as one of the atoms, and it has to be bonded to a highly electronegative atom. The main three highly electronegative atoms we have for hydrogen bonds are fluorine, oxygen, and nitrogen. And one example of that is water, H2O. H2O bonds via hydrogen bonding. So here we have an example of a dipole molecule, or dipole-dipole attraction. So this is CH3Cl. So if you remember from doing polarity, you notice that your hydrogen atoms are your partial positives. So giving that left side there all a positive, partial positive charge there. And your chlorines are partial negative. Okay. So if we have another CH3Cl molecule right next to it. CH3Cl, there you go. Oops. Here's your positive hydrogens and your negative chlorine. All right, as you see, as those two molecules get closer and closer together, there is an attraction. Alright, so that's your attraction there. So the negative chlorine is attracted to the positive hydrogen, and they stick together. So now I mean stick together, I mean stick together like magnets. Okay. The key here is this is not a chemical bond. So no sharing of electrons. Alright. So yeah, usually we do chemical bonds with kind of like the straight lines like this and like this. Okay, when you just have kind of like the dashes like this or the dots, something like that. So yeah, so on a diagram or test, you might just see just some basic dashes. You might see some dots. Okay, that shows that's attraction. So calling this a dipole-dipole bond is kind of a misnomer. It's more like a dipole-dipole attraction, a dipole-dipole force. And this kind of goes on with any other of the molecules. So you can have another one over here, and you have your attractions here, and it can, each molecule can hold on to multiple ones. So you can have a CCl, pardon my sloppy molecule writing here, and it can be attraction here. Right? And so they're just always attracted like that. So it's you can keep adding on and on and on, and that's where you get your attractions. So that's your dipole-dipole attraction. Again, it's an attraction, it's a force. Yes, we do call it a bond, but remember, this is an intermolecular force bond. It's not a true chemical bond, as in like sharing electrons. So that's dipole-dipole. So now this is your hydrogen bonds. So if you look at water, well, water's, hydrogen's partial positive, and your oxygen's partial negative. All right, now what's different here is, oxygen's very electronegative. Very, very electronegative. Plus you have these electrons here, so that just really strengthens that negative charge. So these electrons here, these shared electrons, they're getting pulled towards oxygen quite a bit because that high electronegativity in oxygen. So that negative side here is really, really strong. All right. Now, if you look at the hydrogen end, well, those electrons in this bond, they're getting pulled towards oxygen. They're around oxygen majority of the time. So what's left on hydrogen? Remember, what does hydrogen start out with before it bonds? It starts out with one proton and one electron. Well, if that one electron that hydrogen has, it's getting closer towards oxygen, all you got left is a proton, right? So all you have here is a nice, strong, positive charge. Okay, sometimes they call this an exposed proton because you don't have any negative electrons shielding it. Just a nice plain old proton just out there for the whole world to see. All right, so if you have that, you have your other water molecule here. Again, you got your very strong negative charge there, and your strong positive ends here. So it's a very strong positive here because that exposed proton. You got this highly electronegative, very negative oxygen, plus these unshared electrons. All right, well, what do you think that's going to be? That's going to be a really nice, tough hydrogen bonding force. Right? Again, it's not a chemical bond. There's no sharing of electrons. We just call it a hydrogen bond, just because that's just a common term. But really, it's a hydrogen attraction. And again, it's a very strong dipole because water is polar. It's the positive end of this one polar water molecule, the negative end of this other polar water molecule. So yeah, they're attracted to each other. But yeah, it's a little more specific because it's hydrogen, very strong positive, very strong negative there. So that's where you get your hydrogen bonds, your hydrogen forces, hydrogen attractions. And again, this only works if you have a hydrogen, and this atom right here is oxygen, nitrogen, or fluorine. So that's why, we looked up here, not a hydrogen bond. Because yeah, we got our hydrogens, but hydrogen's bonded to carbon. Okay, carbon's not as electronegative as hydrogen or as nitrogen, oxygen, or fluorine. So it's not as electronegative, not as strong a positive charge on that hydrogen as what the oxygen was. So there you go. So that's where you get your hydrogen bonding. Now the third one is called London dispersion force, and sometimes called LDF. Another term you may have heard, van der Waals forces. So you've heard LDF or van der Waals, they're the same thing. These are very weak intermolecular forces. Exist most commonly with noble gases and nonpolar molecules. Now, there's some other exceptions. We'll talk about the other exceptions there, or some other places you'll see them. But in general, what London dispersion forces does, it's called an instantaneous dipole. It means it just happens instantly, immediately. And then it actually disappears as soon as it's there. Best example I'll show you is with helium. So if you look here with helium, helium has its two protons in the middle, and you get your two electrons. All right. Well, those two electrons that are flying around, well, they don't have to be opposite each other all the time. These electrons move around independently of each other, so they don't care what the other one's thinking. So they're just kind of moving along however they want. Well, at a certain point in time, those electrons are going to pop over to one side. So now what happens is, if they pop over on this left side here, this becomes ever so slightly negative. And since those electrons over there, there's no electrons over here, so this positive charge from this nucleus, it can actually leak out just enough to give a slight positive charge. So you have kind of something that looks like this. Your electrons, 2 electrons over here, and this positive charge nucleus is just enough room to get out that positive attraction. If there's another atom or molecule doing London dispersion forces, happens the same thing, where the electrons shift over here. You're going to get a nice, really small, really tiny, really weak intermolecular force there, and they're going to attract. Now again, as soon as they get over, they're going to shift right back, so that electron can slip back over here, and your weak force all of a sudden disappears. But now keep in mind, this is happening to bajillions of atoms and molecules, so it's always happening. So there's always some sort of LDFs going on somewhere in their sample. And again, these molecules are always, or these electrons are always moving, so they can be here for a brief second, but then in no time at all, they could be back here. So it's constantly negative, negative, not negative, negative, not negative, da da da. So it's going to constantly happen. Enough that for an entire sample, it's always present. So that's how your London dispersion forces work. Now, some other examples I'm working, like with like diatomic molecules. Okay, if you look at oxygen with its double bonds, all right, so that's your Lewis dot structure of your oxygen. Okay, just because they're like that doesn't necessarily mean that those electrons are right there in that spot. Right. So this one, the 2 oxygens, they have the equal electronegativity, so they're equally sharing. But these electrons here in the middle, they're not always 100% in the middle. They can be sometimes over in this area, or they can move over to that side. If they shift ever so slightly closer to 1, again, that gives you a really itty bitty tiny negative. And that gives you itty bitty tiny positive. So that's how some oxygen molecules can actually kind of stick together a little bit. But again, it's so brief, it rarely happens. That's why oxygen molecules don't want to stick together and form into a liquid. They're just not as strong as like your hydrogen bonds or your dipole bonds. So this happens all the time in so all nonpolar molecules we consider LDF. They have LDF intermolecular forces. Okay, so if they're not polar, that's LDF. Okay, so even your methane that we did like CH3 or CH4, exact same thing. Even though it's a molecule, this is a nonpolar molecule, these electrons are constantly flowing around there. So if for some reason the electrons all kind of gather on this part of the molecule, and they all gather on this part of the molecule here, ever so slightly negative here, ever so slightly positive there, you get your attraction. So that's how London dispersion forces work. And yeah, it's all nonpolar molecules. Alright, so the main indicator as to which molecule or compound has a stronger intermolecular force is its melting point or boiling point. Alright, so if a compound has a high melting point or a high boiling point, that means you got to put in a lot of energy for it to change phase, for the molecule to go from solid to liquid, to loosen up those bonds, to turn to liquid, or you got to put a lot of energy in that liquid for the molecules to break apart to go into a gaseous phase. So that's if you have high intermolecular forces. They take higher boiling points or higher melting points, get more energy to change the phase. If they have a very weak intermolecular force, the melting points and boiling points, they're very, very low. It does not take a lot of energy to change phases. So when you look at examples like this, like here we have NH3 and nitrogen, so ammonia and nitrogen, you want to know which one has a higher melting point. Okay, so the higher melting point, which means which one would be a liquid at higher temperatures. I'm sorry, which one will be it will be a gas or a solid at higher temperatures. Okay. So if we look at NH3 versus N2, right? If we look at NH3, sketch out the molecule if you have to. And some of these, if you know these molecules off the top of your head, that's good. If not, you should sketch them to figure out the intermolecular forces. All right, so there's NH3. NH3 is a trigonal pyramid, and NH3 is polar. Not only is it just polar, it is a hydrogen bond. Right? Hydrogen bond because you have hydrogen bonded to a very electronegative nitrogen atom there. So H3 is a hydrogen bond. N2, what's N2? Right, yeah, N2 is LDF, London dispersion forces. It's not polar, not a hydrogen bond. Yes, it's equal sharing of electrons. So the electrons are just kind of moving around, and every so often the electrons might gather more on one end than the other, which makes a very slight positive and a negative end. All right, so NH3 is a hydrogen bond, N2 is a LDF. So which one to have the higher melting point? Which one to be take more energy to turn from a solid to a liquid? And yes, that answer would be NH3, nitrogen, or ammonia. So that have the higher melting point because it has these stronger intermolecular forces. All right, H2O versus H2S. This should be an easy one. There's water. And actually, H2S looks the same thing. Right? Yeah, water. So water is a hydrogen bond. H2S, okay, well H2S is polar. Sulfur's partial negative, hydrogen is partial positive. Right? But it is dipole. So even though it has its hydrogens, sulfur is not as electronegative as oxygen, so it doesn't count as a hydrogen bonding there. It just counts as dipole. So water will have the higher melting point. So that is also why water is a liquid at room temperature, whereas H2S, hydrogen sulfide, is a gas at room temperature. All right, look at a couple others you may see here. All right, Cl2 and I2. Which one have a higher melting point? We can also say higher boiling point. If melting point's high, that means boiling point's also going to be high. It's not where the melting point will be high, but it'll be lower in another case. Right? So they'll both go in the same direction. You can say that. All right, chlorine. So if you look at chlorine, LDF, iodine, also LDF. So which one is higher melting point, higher boiling point? And I'll think of it this way too. Which one would be a solid at room temperature? And you know, chlorine at room temperature, chlorine's a gas. That should be pretty common knowledge. Iodine, at room temperature, iodine's actually a solid. It's a really deep purple colored solid crystal. It looks really cool. So obviously the melting point, boiling point, iodine will be higher. Now why is that? They're both London dispersion forces. So there we got to look at the molecule here. So if we look at chlorine, right, so let's assume if we look at chlorine here, our chlorine has 17 electrons. It is in the third energy level. So I can try to squeeze it here. So there you go. So chlorine has 3 energy levels worth of electrons. Iodine, though, has 5. 1, 2, 3, 4, 5. Now I'm just drawing the one atom. You can imagine them both bonded to 2, and it'll be the same concept. Just for room on the page, I'm just doing one atom here. All right, if you look, here we got all. Now, you might say, oh, because iodine's bigger, it's heavier. That's wrong. Yeah, it's bigger, yes, but that's not because that's not the reason. It's more than that. So you can't just say iodine's bigger. It's because of the number of electrons, or what we call electron density. And when you look at chlorine, chlorine has 17 electrons in just its one. Okay, iodine has 50 something. Let me look it up. 53. I knew that. Iodine has 53 electrons. Okay. So you got 17 electrons. If all 17 electrons are here, or at least most of them, all right, that'll give you a negative charge there. Whereas here, iodine, if you get most of the 53 electrons here, you get a lot stronger negative charge. And then you have a 53 proton positive charge here versus a 17 proton charge here. Positive proton or positive charge there. All right, so the higher electron density equals a stronger negative charge. So it's a little bit stronger negative charge, and on the opposite end you get a stronger positive charge, so that makes it a stronger attraction. And where if you have a lower electron density, less electrons here, less protons here, it's really not that strong of attraction, so that's going to be a little bit weaker. So that's why, so yes, iodine's bigger, but it's more than just bigger. It's bigger, meaning you have more electrons, gives you a stronger negative charge, and more protons give you a little bit stronger positive charge. So that's how it works. Yeah. So if they're the same intermolecular forces, next step is you go by the size. But remember, the size just means greater or less electron density, not just because it's heavier. Okay. Same thing here, propane and hexane. So if you look at propane, it's C3H8. 2, 3, 4, 5, 6, 7, 8. So these are all hydrogens here. All right. So that's propane. Hexane, 3, 4, 5, 6. And I'm not going to draw hydrogens on all these. I'm just going to do this. Assume there's hydrogens on each of those. All right, so same thing. Hexane is going to have a higher intermolecular force. And hexane is pretty much a liquid at room temperature, where propane is basically a gas at room temperature. Yeah, hexane, because it's a lot larger, you got more areas where the electrons can shift from one side to the other, so you have a larger electron density. So this one will work. All right, let's look at a couple others here. Here I have propane, just like before. Here I have something else called propanol. So, which one? Well, we'll change the question up a little bit. Which is a liquid at room temperature, 25 degrees Celsius. All right. So, yes, it would be propanol. This would be the winner. And why is that? Yeah, propane is LDF, whereas propanol is hydrogen bond. Okay. Now, right, the whole thing isn't a hydrogen bond. What we say is this is an area of hydrogen bonding. The rest of this area is what, like over here? Yeah, that's more like an LDF type of area because it's all positives here and the negatives kind of buried in the middle there in the carbon. Here, you have a negative end, the very strong negative end, pulling those electrons from the carbon and the hydrogen. So yeah, so you have a negative end here and a positive end there. So that negative end there makes it a little bit stronger when it comes to intermolecular forces. So yeah, so propanol is a liquid at room temperature, and it's because of that hydrogen bonding area there. And it has nothing to do with size. Sometimes you get that, well, propanol has a greater mass because you have an extra oxygen there. It's like, no, it's because of LDF versus hydrogen bonding. All right, so about something like this. I know the red color kind of gave it away. So this would have higher intermolecular forces. Or not say, better word, stronger intermolecular forces. Right? And that is because you have, I like to call it, two areas of hydrogen bonding. So you got your negative area over here and also a negative area over there. So those two negative areas will be attracted to any of the positive hydrogens coming close to it. Now you say, well, isn't this a non-polar molecule because you got negatives on both sides? Well, not exactly, because this molecule is actually kind of large there. So when you get larger molecules, and what we did in the last chapter, then we designate different areas of polarity. So this is a polar area and this is a polar area. So they really don't cancel each other out, because in the grand scheme of things, if you look really closely at a molecule, those two are far apart enough that they don't even affect each other. Okay. So here we got two areas of hydrogen bonds versus just one. All right, last example we see here. All right, I'll let you count this on your own later. Both of these molecules are C6H14. All right, but yeah, cool thing about carbons are, and when you take organic chemistry, you'll see that carbons can form a multitude of different structures. That's why organic chemistry is so much fun. All these different structures you get to learn. So, two C6H14 molecules. All right, intermolecular forces wise, they're both the same thing, LDF, right? So we can't say electron density wise one is technically more than the other because it's got the same number of hydrogens. Right. The one with the higher melting point, or boiling point, which means has the stronger intermolecular forces, would be this one. Okay, and the one on the right will be a little bit lower. So one on the right will become a gas at a much lower temperature than the one on the left. Okay, the reason for this is, you kind of think surface area. That'd probably be a good thing to think of. All right. 4, 5, 6. Okay, if you look at this, more areas where they can connect. Kind of like a greater surface area. So if all these hydrogens all of a sudden became, if all the electrons shifted up here, even most of them, doesn't have to be all of them, all right, that gives a lot of negative area here. So a stronger negative area will be attracted to this, making it a little bit tighter. Okay, whereas, if you look on this side, 1, 2, 3, 4. All right, you only just have a smaller area where they can kind of bump into each other because it's more round. All right, just kind of think, you take two sticks and lay them flat on each other, you've got a lot of surface contact between the two. But if you take two balls, it's like two beach balls, golf balls, or put them together, it's just like one little point there. So yeah, so you get more compact, you get less areas where they can kind of come in contact with others. So that just does not create as strong as a positive and negative attraction there. Yeah, so the longer, more straight carbon chains, those tend to have higher melting points. Okay, those tend to be stronger intermolecular forces. And that is your intermolecular forces.